So Jim Moffett's next, and he's gonna, from University of Southern California, my old stomping grounds, and he's gonna give us some insights into the Indian Ocean biogeochemistry coming out of the recent geotraces work. So Jim, take it away.
Okay, let's see, have I got this placed right? Can everybody hear me? Yes, I'm going to talk a little bit about what geotraces, that's the other program that's going on, hasn't had much play yet in this conference, but it does have an active presence in the Indian Ocean, so I would like to do that. I'm also going to provide a little background information first, based largely on some of my own work, and Dennis's introduction, particularly focusing on the JGOFS program, was really useful in that regard. So I'd like to give an overview of how monsoon-driven processes in the Arabian Sea relate to iron limitation, something that you wouldn't have heard about in Dennis's talk because the iron hypothesis was, for a variety of reasons, was never actually tested in that program. I'm also going to talk about the dynamics of metal cycling within the Arabian Sea oxygen minimum zone. As Dennis pointed out, this is a highly dynamic environment that applies to metals. It's indeed the most dynamic place that I've ever studied. I'd also like to talk, moving on to some of the new novel findings from geotraces, the importance of the oxygen minimum zone and hydrothermal inputs of iron into the basin. So this is expanding on a lot of work that is being carried out by geotraces programs globally to try and learn more about the sources and sinks of iron in the oceans. I'd like to show what I think is a very interesting analogy between the Japanese meridional transect through the Arabian Sea into the southern Indian Ocean and a geotraces cruise that the U.S. mounted in 2013 in the eastern tropical South Pacific. And in the same vein that was done for that program, conduct an assessment of the importance of hydrothermal sources of iron to the Southern Ocean. I'd also like to give you a brief survey of some of the major unanswered questions and a summary of the activities of the Indian Geotraces program as well. So first off, as Dennis pointed out, if you're interested in biogeochemical processes in the Indian Ocean basin, you're drawn to the Arabian Sea during the southwest monsoon. It is hands down like the most important feature there. And of course, this is a satellite image from the month of August, which is sort of the height of the southwest monsoon, the time when primary production is the greatest. Now, a big conclusion of all of these JGOFS cruises that took place in the 90s was that iron limitation was not important. Indeed, there's some quote attributed to Sharon Smith that I've never actually been able to find, but everybody tells me about it, where she said that the Arabian Sea is Mother Nature's iron enrichment experiment, therefore attributing this vast biological productivity there to the fact that it's surrounded by arid lands and there's a lot of supply. And it's the one place where iron would be truly plentiful. I was out there in 2004 with Waji Naqvi, who is sitting over here, the director of the National Institute of Oceanography in India, and I started looking at the regional geography and was really struck by the fact that off the coast of Oman, which is where all of the upwelling and nutrient supply occurs during the southwest monsoon, it looked a lot like other coastal upwelling regimes where iron limitation is really important, like the central California coast, Peru, and so forth, in that there were several important features. One, very strong episodic upwelling, and you can see these low temperature regions right along the central Omani coast there. Secondly, very narrow shelves. So the areas where the upwelling is greatest, the shelf is very narrow. So there's very little opportunity for upwelled waters to entrain iron into these systems and advect it offshore. That's in contrast to places perhaps further north where the shelf is wider. This is a very important distinction that Ken Brulin and others identified, Ken Johnson in the Central California and Peru coast, and so it seemed likely that this would be the case. And I started thinking about this. The other thing an extremely important finding from the Jagoff's era was that silica becomes very strongly depleted relative to nitrate during the southwest monsoon. That's a very important diagnostic of preferential drawdown of silica and nitrogen by iron-limited diatoms. And this goes back to some work, observations originally made by Dave Hutchins. Iron-limited diatoms have very high silica to nitrogen ratios. So those two things were very interesting. Now, before I had an opportunity to get back there, Jerry Wiggert did some really nice modeling studies where he also showed that you have a massive amount of export in these areas, and even though you have a high source of iron from the atmosphere in the Arabian Sea, it's not enough to avoid moving into an iron-limited condition. So now some of you with long memories might remember that I actually showed some of these data previously at an OCB meeting about 7 years ago, so I'm not going to spend a lot of time on it. But that was pretty much right after we got back. So this was a cruise, again, led by Waji on the Roger Revelle, a very interesting cruise, both scientifically and culturally, as you might imagine. And this was basically covering some of the same stations occupied by Jagoffs in a sort of a quasi-zonal transect across the Arabian Sea, including the parts of the oxygen minimum zone to the right and areas which are not in the oxygen minimum zone but are dominated by upwelling further west. This is just a quick way of summarizing these data. At each of these points here represents a station where I collected surface water samples, did the classic John Martin style iron incubations, and looked at the biological response. What the color chart shows here is the ratio of chlorophyll in the iron-treated samples compared to the control, and the values ranged from sort of minimal effects, typically at stations where nitrogen and nitrate was already very low, to values as high as a 6-fold increase in the chlorophyll. The numbers there represent the concentrations of iron in the surface waters, which, although they're not exceedingly low, they're the kind of values that, for example, Rulin would see in iron-limited places in Central California. The other thing that was so in other words, just about everywhere we went, particularly towards the west as we got into these cold, freshly upwell waters, we saw a substantial response. The other thing that was highly characteristic of this area and atypical for these types of experiments was that the response to iron was dominated by a single phytoplankton, Phaeocystis. And that's because, like I just told you a few minutes ago, the silicate was so strongly depleted in these waters. That's a real feature that there's nothing for diatoms to grow with. So you get massive appearance of colonies of Phaeocystis, a lot of DMS production associated with Phaeocystis as a consequence of adding iron to these systems. So kind of a summary of that part of this survey was that everywhere we looked, we saw iron limitation during the southwest monsoon. This Phaeocystis production was the characteristic response. And the other thing that I have to mention is that one thing that sort of motivated us to do this and I think was why it didn't get looked at in Jagoffs was that our iron numbers in surface waters were much lower than the ones reported by measures in Vink. If you just took their data at face value, you wouldn't conduct these experiments. The values were too high. They had trouble, as many of you who participated in that might have known. They lost their trace metal CTD, the cruise prior to the critical southwest monsoon cruise, which I think was TN050. So all their samples came from the ship's rosette. And we now know through a lot of work with geotraces and intercalibration and so forth that you really can't get a clean iron sample from the ship's rosette. So that was at least I think a part of the explanation for this problem. Now, why is this important from the standpoint of monsoonal variability? Well, As Dennis and Mike pointed out, the southwest monsoon is driven by low pressure over the Asian landmass. This is intensifying as the albedo associated with the ice pack is decreasing. The land masses are becoming increasingly warm. And that decreasing albedo, of course, represents positive feedback. An important negative feedback that Joachim and his coworkers identified or proposed was that increasing the strength of the southwest monsoon would bring more nutrients to the surface and increase productivity and carbon export. To assess how changes in dust might affect that scenario, I'd like to just sort of give you this is a conceptual picture of something that Dennis already showed. Unlike, say, Peru, the maximum carbon export, and this comes from Ken Bissler's work in Jagoff's, is to the west, because that's where the upwelling is, that's where all the nutrients are high. But the water on the western side is well ventilated, and we know that, for example, going back to work by Raina Fine and Don Olson. The more poorly ventilated or sluggish circulation is to the east, and that's where the OMZ actually accumulates, even though carbon export is a lot lower on that side. A very different scenario than you would see in Peru or other areas. So what might happen if we increase the dust flux? Well, the most likely scenario, if we increase dust flux associated with, say, an intensifying monsoon and more transport, perhaps from like Somalia or somewhere like that, would be more primary production, a higher primary production occurring in the west, more carbon export, fewer nutrients making it over to the east. This might lead to a westward expansion of the oxygen minimum zone. And in fact, we do see seasonal expansions and contractions of the OMZ that occur on multi-year timescales. There's a very nice paper by Tim Rickson recently published that kind of explains that. On the other hand, with fewer nutrients making it over to supply carbon export on the side of the Arabian Sea where the circulation is sluggish enough for the OMZ to manifest itself, there might be actually less supply of organic matter on that side, and therefore we might wind up with an OMZ that's larger but less intense, possibly even one that's no longer denitrifying, like we see in the Bay of Bengal. This is all pretty speculative. I think another thing we might throw in here is that DMS fluxes might be affected in some way. Again, that's sort of hard to predict how that scenario would go. But when I presented this to OCB pretty much right after the cruise, though, I didn't really know much about what might be going on with metals in the interior. All I reported then were those surface iron data that I showed in that previous slide. Subsequent to that, I was able to get some support actually to do some of the analyses of these, and I'll discuss that in the acknowledgments of the water column data across that section. These are some plots here for our section of salinity, temperature, nitrite, and oxygen. They don't look that different from the ones that Dennis showed. The oxygen minimum zone clearly is to the east here with a well-defined secondary nitrite feature, a large oxygen minimum zone, and then the more well-ventilated waters to the west. What these data show here is the concentration of total dissolved iron at the top there, and you can see that the iron is clearly higher to the west or to the east than it is to the west. But it's not some sort of monolithic feature that correlates exactly, for example, with nitrite. Nevertheless, the concentrations are quite high, and part of the reason for that is that a significant fraction of the iron is present as iron 2 which is very, very soluble, and that helps increase the residence time. Nevertheless, I think an important feature there is that there's a big front just to the west of 66 degrees east in the iron concentration, with much higher concentrations to the west of that. That seems to be associated with a, I should just use the pointer here, with a low salinity water mass here, or relatively low salinity water mass here, which kind of suggests that if you're interested in iron budgets in this system, things that affect the expansion or contraction of the oxygen minimum over here might have less of an effect than whatever is controlling the characteristics of that water mass. So I think that's an important part of this. Nevertheless, we do see a lot of structure, very strong ferrocline here, which Dennis alluded to in terms of seasonal export and removal of iron. In fact, the excess of iron here relative to the deficit here is can probably be accounted for by that seasonal transport. As I mentioned, this is one of the most dynamic places I've ever been, but a ferrocline like that isn't necessarily all that unusual. People, who work in the Southern Ocean, like Phil Boyd, would have seen features like that in various places. But here's one that is. This is a profile of copper, and those of you know copper is one of my favorite elements, but if you're just interested in the distribution of copper in the ocean, it's kind of boring. It has an almost linear increase with depth. Over this sort of depth range, it would probably hardly change at all in most places, except in the Arabian Sea. I've never seen anything like this anyplace else. You have stripped out copper up in the surface water, a very high concentration of copper in the lower oxycline and at the top of the oxygen minimum zone. And then you have a big deficit within the oxygen minimum zone itself. Again, I've never seen anything like that. I think it's intimately related to iron limitation in Phaeocystus. Maite Maldonado has shown that Phaeocystus has a massively high requirement for copper, very anomalous high copper to carbon ratios. So the sinking biomass there is strongly enriched in copper. Waji Naqvi's argued that Phaeocystus biomass is rapidly remineralized at very shallow depths in the Arabian Sea. And so a lot of that copper is being injected into this feature here. But what's going on there? Why is it so low within the core of the oxygen minimum zone? I think there's two reasons. Uptake of copper within the core there could reflect uptake by denitrifiers. Copper is critical in several metalloenzymes that are important in denitrification. So there's a high biological demand, but it might also be taken up by sulfide-bearing sinking particles. And there's quite a bit of interest within the trace metal community in this particular scavenging mechanism as well. Not because this is a sulfidic area, but because sulfide-bearing microenvironments might be present in those types of particles. Now you might think, well, is this something that we would see in the Peru upwelling, the Mexican upwelling? Those are also highly dynamic environments. And the answer is only slightly. There is no place like the Arabian Sea that is as massively, and I think Dennis would probably agree with me, as exciting in terms of the actual rates of these processes. Waji Naqvi has collected water from the top of the oxygen minimum zone that still has quite a bit of nitrate in it, just leaves it in an incubation without adding any organic matter, and a few days later, the nitrate is all gone. I mean, that's something that you just don't see anyplace else, making this a very exciting place to work. Now, I've already been through a lot of my talk and haven't said anything about geotraces. How does geotraces inform any of this type of work? This is the geotraces data I'm going to report from the Japanese geotraces expedition in 2009. I participated on this looking at iron 2. My postdoc Yoshiko Kondo was on the cruise. This was the first meridional section in the Indian Ocean conducted in the geotraces program. It included the Arabian Sea oxygen minimum zone as well as the Rodriguez triple junction hydrothermal system. And I'm going to be focusing almost entirely on iron at this point. Here are the results published by Jun Nishioka in Earth and Planetary Science Letters a couple of years ago. And what you can see here is that, well, I'll show you this first. The first 3 stations here were in the oxygen minimum zone. Oxygen is highly depleted, and you can see the oxygen minimum zone feature, at least with low oxygen, extends almost all the way through, or it's detectable almost all the way through the section. Iron is quite elevated within the oxygen minimum zone, and some residual amount of that iron is detectable all the way down here to station 9. But you can see here that that feature doesn't persist all that far south. It certainly doesn't mirror the oxygen minimum zone. It's not this, in other words, iron transport out of this basin is not oxygen dependent. And only within that region itself does the presence of iron 2 provide some type of lift. The more important feature emerging from the Arabian Sea is at a much greater depth where oxygen is present, and it merges with what Nishioka attributed to a hydrothermal source from the Rodriguez triple junction at this point here. Just to summarize, high iron within the oxygen minimum zone drops off rapidly south of the main part of the OMZ. The deeper plume from the oxygen minimum zone, between 1,000 and 3,000, extends much further offshore. And it's hard to say how far that would have gone because it merges with another plume that's associated with hydrothermal inputs. Now, just summarizing those features there, does any of that sound familiar? Particularly for any of you who are interested in the Geotraces program. And I would argue that yes, I think many of you may have seen this before. These are iron data generated by Pete Sedgwick's group at Old Dominion, which are results of the Geotraces, US Geotraces GP16 section, characterized by, again, a big plume of iron that's associated with an OMZ, but actually beneath that OMZ, and a hydrothermal plume extending further out. The big difference here is that this hydrothermal plume is much further away. We did not follow the core of that plume. It extends off somewhere else. So we don't actually, these are separated by an area where the concentrations of iron are relatively low. Is this system relevant at all to the Arabian Sea? I'd argue that it is, first by looking at some of the basic features of that plume. So this again is this big dissolved iron plume plotted on ODV using Sedgwick's data. The color scale is off here because we have to fit in these shelf data, which are exceedingly high, about 30 nanomolar or so. I'm not showing oxygen here, but basically the low oxygen area is up there. And it does play a role in this plume, but you can see that there is a massive amount of iron coming off the shelf here, that particularly here, that is not oxygen dependent at all. Here's some iron too, and again, that big feature there doesn't really depend on the presence of this soluble reduced iron directly. So what might be going on here? Well, we've sort of got this emerging idea amongst those of us who participated in this cruise that the iron too is kind of important in helping that iron sort of get off the shelf. After that though, Phoebe Lamb and her group have shown that particulate iron forms within this oxygen minimum zone as iron oxides, sinks down onto the shelf here, and probably undergoes reduction because these are still highly reducing sediments, and gets advected offshore. Now the great thing about a Geotraces cruise is that you have all the supporting data that on other cruises you wish for but don't actually have. So for example, on our cruise, we have radium-228 data where, of course, and radium-228 is a diagnostic for shelf sources, and we have a nice plume here of radium-228 that corresponds really well with that particular feature. Now, why might this be relevant for the Arabian Sea? Well, a big factor here, in order to get mobilization of iron off those slope sediments, is that they have to be reducing sediments. And that means there has to be active sulfate reduction taking place in those sediments. This is a model here of depth integrated sulfate reduction rates generated by Bowles et al. This is the Kai Henrichs group in Bremen. And you can see here that many parts of the ocean have sulfate reduction rates that are, of course, a function of organic matter, bottom water oxygen concentration, and so forth. But the Peru area here, where we did our section, and then the Arabian Sea in particular, are hotspots for this. So it seems highly likely that benthic sources of iron are important in the generation of that plume and its transport offshore. And it's disconnected from the oxygen minimum zone itself. Nevertheless, the oxygen minimum zone may play a very important role in getting material off the immediate coastal area and onto those slope sediments in the first place. Now, the next step, which is also an exercise we went through in the U.S. cruise off of Peru, is who cares? Who cares about a big plume of iron in the subsurface, other than those of us who just happen to be interested in iron? So a big question is how much of that iron might ultimately make its way to the Southern Ocean. And we can do the same approach that we did in that expedition here. And so just the other day I asked Tim DeVries to run a simulation with an inverse model that he has about what fraction of the water where this iron is high in the Indian Ocean might actually make its way an outcrop in the Southern Ocean. So again, this is along the 70 East Meridian, and you can see here that where a lot of that material is, even over here in the oxygen minimum zone, about half of that water might be expected to outcrop. Key issue there is the time frame. I mean, for example, some of this water might take 800 or 900 years, and perhaps all the iron would be gone by then. There does seem to be a kind of a sweet spot here where some of the iron in the oxygen minimum zone might make it down to the Southern Ocean in a much shorter period of time. Okay, thanks, Jerry. Yeah, I'm almost done. And I'm just sort of showing where those areas are here. So think about this area here corresponds with that area there. The person who's sort of done the most work on this is Al Talliaboy from the UK, and he sort of made some calculations about how these various hydrothermal sources, including the Indian Ocean source defined or identified by the Japanese, might be important, and the kinds of ballpark numbers that he's coming up with are as high as 30% of the carbon export in this area could be assisted, if you will, by hydrothermal sources of iron. Now, one thing I should point out, though, is that Al has been focused solely on the hydrothermal sources now. He hasn't looked at the impact of these oxygen minimum zone associated plumes. Let's see, I think I'll skip these two. And I'd like to just talk about two more things. I think in terms of future work, we need to assess where the hydrothermal plume goes and how quickly iron is removed. One thing that is, I think, very clear to many of us is that Japanese section is extremely important. It may have to be repeated by somebody because the resolution that they had was not that great, and they missed a critical section because they had to escape a pirate as well when they were. I think they were one of the last cruises during that really high pirate area. We need more data from shelf and slope regions to assess benthic and riverine sources. Full water column sections from the Bay of Bengal are needed. We don't really have a good sense of its role as a source of iron. We need to characterize the chemistry of the Red Sea overflow water because that's a source of water that gets upwelled off of Oman. And this is important, but not practical. doing coastal work off of Yemen and Somalia is probably still a bad idea. And finally, we need more work to characterize the diversity of hydrothermal sources in this region. Some of that data may already be available, although I haven't seen it yet. There is a big GeoTraces India program that's being centered at PRL in Ahmedabad. Sunil Singh is in charge. They've done a bunch of cruises already covering all of these really cool places to answer a lot of these questions. Sunil hasn't sent me any data. He did give a presentation at Goldschmidt apparently, but pretty much if you look at what they're doing, this is kind of a laundry list of all of those critical things that, that I think we would need. And I think with that, I'll wrap things up. So thank you.
Give people some direction here.
Okay,
Oh, go ahead.
so
Yeah.
I think we'll hold questions for Jim for lunch and,
Discussion session too.
or the discussion in the afternoon. And I want to also thank our speakers again for this Indian Ocean session we've had so far.